Imagine standing on a planet where the gravity is nearly 3 times that of Earth, where the sun in the sky is a dim, red ember, and where the atmosphere is thick with hydrogen and helium. This isn't the stuff of science fiction. This is a real possibility on a super-Earth. And just as fascinating, there are mini-Neptunes out there, worlds that could be shrouded in thick atmospheres, with oceans of liquid diamond or exotic superionic water. These aren't just distant dreams. They're real classes of planets that astronomers are discovering in droves. In this video, we're going to dive into the mind-blowing world of super-Earths and mini-Neptunes, exploring how they form, what they're made of, and why they matter. So, buckle up, because we're about to take a journey to some of the most exotic worlds in our galaxy. Definition of super-Earths. Super-Earths are a fascinating class of exoplanets that have captured the imagination of astronomers and space enthusiasts alike. These planets are defined by their size, which is larger than Earth's but smaller than that of ice giants like Neptune. Typically, super-Earths have masses ranging from about 1 to 10 times that of Earth. Their sizes can vary, but they generally have radii between 1.25 to 2 times that of Earth. One notable example is Kepler 442b, which orbits within the habitable zone of its star, making it a prime candidate for further study in the search for life beyond our solar system. The formation of super-Earths is still a topic of ongoing research, but several theories have been proposed. One prominent theory suggests that these planets form in the protoplanetary disk around a young star, where they accrete enough material to become larger than Earth, but not massive enough to become gas giants. Another theory posits that super-Earths may form closer to their host stars, where the higher temperatures and densities of the protoplanetary disk allow for more rapid accretion of solid material. The diversity in their compositions adds another layer of complexity, with some super-Earths likely having rocky surfaces similar to Earth, while others might possess thick atmospheres or even global oceans. Comparing super-Earths to mini-Neptunes reveals intriguing differences and similarities. Mini-Neptunes, also known as sub-Neptunes, are another class of exoplanets that are slightly smaller than Neptune but larger than Earth. They typically have radii between 2 to 4 times that of Earth and are thought to have thick hydrogen-helium atmospheres. In terms of size, super-Earths are generally smaller than mini-Neptunes, but their compositions can overlap. Some super-Earths might have rocky cores with substantial atmospheres, blurring the line between the two classes. Understanding these distinctions is crucial for astronomers to better categorize and study the diverse array of exoplanets discovered in recent years. Characteristics of super-Earths. Super-Earths are a fascinating class of exoplanets that have captured the imagination of astronomers and space enthusiasts alike. These planets are typically defined as having a mass and radius larger than Earth's, but smaller than that of ice giants like Neptune. They can be up to 10 times more massive than Earth, and their sizes range from about 1.25 to 2 times that of our home planet. One notable example is Kepler 442b, which orbits within the habitable zone of its star, making it a prime candidate in the search for extraterrestrial life. Another is 55 Cancri e, a densely packed planet with a surface that might be covered in lava. Their compositions vary widely, with some being rocky like Earth, while others might have significant amounts of water or other volatiles. This diversity makes them a hot topic for research, as they challenge our understanding of planetary formation and evolution. The formation of super-Earths is still a subject of ongoing debate. One prominent theory suggests that they form in the protoplanetary disk in a manner similar to terrestrial planets, through the accretion of solid materials. However, their larger sizes and masses imply that they might have formed in regions with higher densities of materials or through more efficient accretion processes. Another theory proposes that super-Earths could be the remnants of once giant planets that lost their gaseous envelopes due to stellar radiation or other processes. This would explain why some super-Earths have dense, rocky compositions, while others might retain significant atmospheres. The discovery of super-Earths in tight orbits around their host stars also suggests that they might have migrated inward from their original formation locations, adding another layer of complexity to their formation stories. Comparing super-Earths to other planet classes reveals intriguing differences and similarities. Unlike mini-Neptunes, which are smaller versions of ice giants with thick atmospheres. Super-Earths can have a wide range of compositions. Some might be rocky with thin atmospheres, while others could have substantial water layers or even global oceans. Their sizes and masses place them in a unique category, distinct from both terrestrial planets and gas giants. For instance, Kepler 22b, a super-Earth, has a radius about 2.4 times that of Earth and orbits within the habitable zone of its star. In contrast, Mini-Neptunes like K2-138c have radii around 1.6 to 3.5 times that of Earth and are likely enveloped in thick atmospheres of hydrogen and helium. This diversity in composition and structure makes super-Earths a crucial area of study for understanding the broader spectrum of planetary types and their potential habitability. Formation of super-Earths. Super-Earths and mini-Neptunes are two new classes of planets that have been discovered in recent years thanks to advancements in astronomical technology. Super-Earths are planets with masses ranging from about 1 to 10 Earth masses, while mini-Neptunes are slightly larger, with masses between 10 to 30 Earth masses. These planets are not found in our solar system, but they are common in other planetary systems. For instance, the planet Kepler 442b, located about 1,200 light-years from Earth, is a prime example of a super-Earth. It orbits within the habitable zone of its star, making it a potential candidate for hosting life. Similarly, mini-Neptune Kepler 138d, also discovered by the Kepler Space Telescope, is enveloped in a thick atmosphere, likely composed of hydrogen and helium. The formation of super-Earths is still a topic of ongoing research, but several theories have been proposed. One prominent theory suggests that these planets form in the protoplanetary disk, where dust and gas coalesce to form larger bodies. Unlike Earth, which formed from the accretion of solid materials, super-Earths may have formed from a combination of rock, metal, and volatile compounds. This mixture allows them to grow larger than Earth, but not as large as gas giants like Jupiter. Another theory posits that super-Earths form closer to their host stars, where the higher temperatures and pressures facilitate the rapid accumulation of materials. This proximity to the star also influences their composition, as the intense heat can vaporize lighter elements, leaving behind a denser, more rocky core. Comparing the sizes and compositions of super-Earths and mini-Neptunes reveals significant differences. Super-Earths are typically more dense and rocky, with a composition similar to Earth but scaled up. Their larger size means they can retain a thicker atmosphere, which can be rich in water vapor, carbon dioxide, or other gases. Mini-Neptunes, on the other hand, are less dense and have a significant portion of their mass in the form of gases. Their atmospheres are thicker and more extensive, often enveloping a core that may be rocky or icy. The exact composition of these atmospheres is still being studied, but they are thought to contain a mix of hydrogen, helium, and other volatile compounds. These differences in size and composition have important implications for the potential habitability of these planets. While super-Earths might have conditions more akin to Earth, mini-Neptunes are likely to be less hospitable due to their thick, potentially toxic atmospheres. Detection methods for super-Earths. Super-Earths and mini-Neptunes are two new classes of planets that have captivated astronomers and planetary scientists alike. Super-Earths are planets with masses ranging from about 1 to 10 Earth masses, while mini-Neptunes are slightly larger, with masses up to around 15 Earth masses. These planets are not found in our solar system, making their study particularly intriguing. Examples of super-Earths include Kepler 442b and LHS 1140b, while mini-Neptunes include planets like Kepler 11d and GJ 3470b. Formation theories suggest that super-Earths could be either rocky planets with a higher density than Earth or water worlds with a significant amount of water or other volatiles. Mini-Neptunes, on the other hand, are likely to have a thick hydrogen-helium atmosphere surrounding a rocky or icy core. Detecting these planets is a complex task, but several methods have proven effective. The most common technique is the transit method, which involves measuring the dimming of a star's light as a planet passes in front of it. This method is particularly useful for detecting planets around relatively small and cool stars. For instance, the Kepler Space Telescope has identified numerous super-Earths and mini-Neptunes using this technique. Another powerful method is the radial velocity technique, which detects the wobble of a star caused by the gravitational pull of an orbiting planet. This method is more effective for detecting larger planets or those orbiting closer to their stars. The High-Accuracy Radial Velocity Planet Searcher, HARPS, spectrograph has been instrumental in discovering many of these planets. In addition to these methods, astronomers also use transit timing variations, TTVs, and gravitational microlensing. TTVs occur when a planet's transit times vary due to the gravitational influence of another planet in the system. This method has been used to confirm the presence of additional planets in systems already known to host super-Earths or mini-Neptunes. Gravitational microlensing, although less common, can detect planets by measuring the brightening of a star's light as a planet passes between it and an observer. This method has led to the discovery of planets like OGLE 2005, BLG 390lb, a cold super-Earth. The study of super-Earths and mini-Neptunes is still in its infancy, but the data collected so far has provided valuable insights into planetary formation and evolution. These planets offer a unique opportunity to understand the diversity of planetary systems and the conditions that might lead to the formation of habitable worlds. As detection methods improve and new telescopes come online, our understanding of these fascinating planets is sure to grow. Notable examples of super-Earths. Super-Earths and mini-Neptunes represent two new classes of planets that have expanded our understanding of planetary diversity beyond the traditional categories of terrestrial and gas giants. Super-Earths are planets with masses ranging from slightly more than Earth's to about 10 times its mass. They can be rocky, like Earth, or have a significant amount of water or other volatiles. Mini-Neptunes, on the other hand, are smaller versions of ice giants like Neptune, with masses up to 10 times that of Earth and thick hydrogen-helium atmospheres. These planets often have radii between 2 and 4 times that of Earth, placing them in a size range not found in our solar system. One of the most notable examples of a super-Earth is 55 Cancri e, which orbits a sun-like star in the constellation Cancer. This planet is about 8 times the mass of Earth and has a diameter just over twice that of Earth, suggesting a dense, rocky composition. Its extremely close orbit to its star results in surface temperatures high enough to melt metal. Another intriguing super-Earth is LHS 1140b, which orbits within the habitable zone of a red dwarf star. With a mass about 6.6 times that of Earth, it is a prime candidate for further study to determine its atmospheric composition and potential habitability. Kepler 442b is another example, often referred to as a superhabitable planet due to its location within the habitable zone of its star and its potential to have conditions more suitable for life than Earth. The formation of super-Earths and mini-Neptunes is still a topic of ongoing research. One theory suggests that these planets form in the protoplanetary disk through the accretion of dust and gas, similar to the formation of terrestrial planets. However, their larger sizes and different compositions indicate that they may have formed in different environments or through different processes. For instance, some super-Earths might have formed closer to their stars, where the higher temperatures and pressures allowed for the accumulation of more massive cores. Mini-Neptunes, with their thick atmospheres, might have formed farther out in the disk, where ices and gases were more abundant, and then migrated inward. Comparing the sizes and compositions of super-Earths and mini-Neptunes reveals a fascinating diversity. Super-Earths can range from dense, rocky worlds to planets with substantial water or gas envelopes. Some may even have global oceans beneath thick atmospheres. Mini-Neptunes, with their significant atmospheres, are less dense and have radii that place them between Earth and Neptune in size. The compositions of these planets can vary widely, with some having rocky cores surrounded by thick atmospheres of hydrogen and helium, while others might have significant amounts of water or other volatiles. This diversity challenges our understanding of planetary formation and evolution, highlighting the need for further exploration and study. Habitability of super-Earths. Super-Earths and mini-Neptunes are two new classes of planets that have captured the imagination of astronomers and the public alike. Super-Earths are planets with masses ranging from slightly more than Earth's to about 10 times that of Earth. They can be rocky, like Earth, or have a significant amount of gas in their atmospheres. Examples of super-Earths include Kepler 442b, which orbits within the habitable zone of its star, and 55 Cancri, which is so close to its star that its surface may be a lava ocean. Mini-Neptunes, on the other hand, are planets with masses similar to Neptune's but much smaller radii. They are likely to have thick hydrogen-helium atmospheres. Examples include Kepler 11f and GJ 3470b. The formation of these planets is still a topic of ongoing research. Super-Earths may form from the accretion of rocky material, similar to Earth, or from the migration of larger planets that lose their gas atmospheres. Mini-Neptunes might form from the rapid accretion of gas onto a rocky core, or from the migration of larger planets that retain their gas atmospheres. In terms of size and composition, super-Earths can vary widely. Some may be rocky with thin atmospheres, while others might have thick atmospheres and even global oceans. Mini-Neptunes, meanwhile, are likely to have thick atmospheres and may not have a solid surface. Their compositions can range from water-rich to gas-dominated. When considering the habitability of super-Earths, several factors come into play. The most crucial is the planet's position within the habitable zone of its star, the region where liquid water could exist on the surface. However, other factors such as the planet's atmosphere, magnetic field, and geological activity also play significant roles. For instance, a thick atmosphere could help regulate temperature and protect the planet from harmful radiation. A strong magnetic field could shield the planet from stellar winds and cosmic rays. Geological activity could cycle nutrients and maintain a stable climate. Some super-Earths, like Kepler 442b, are within the habitable zones of their stars and have been touted as potential candidates for hosting life. However, it's important to note that habitability does not necessarily mean that life exists or has ever existed on these planets. It simply means that conditions might be right for life as we know it. Moreover, our understanding of habitability is based on Earth-centric models, and life elsewhere might have different requirements. The study of super-Earths and mini-Neptunes is still in its infancy, and there's much we don't know. For example, we don't yet understand how common these planets are, or how they form and evolve. We also don't know if any of them are truly habitable, or if life could exist in the extreme conditions found on some of these worlds. However, with the advent of new telescopes and instruments, such as the James Webb Space Telescope, we're poised to learn more about these fascinating planets in the coming years. Each new discovery brings us one step closer to understanding our place in the universe and whether we are alone in it. The search for habitable worlds is not just a scientific endeavor, but a deeply human one, driven by our curiosity and our desire to explore. Definition of Mini-Neptunes. Mini-Neptunes are a class of exoplanets that have captured the attention of astronomers and astrophysicists alike. These planets are typically defined by their size, which is larger than Earth but smaller than Neptune. Specifically, Mini-Neptunes have radii ranging from about 2 to 4 times that of Earth. Their masses can vary, but they are generally less massive than Neptune, which is about 17 Earth masses. One notable example of a mini-Neptune is Kepler 11f, a planet discovered by the Kepler Space Telescope. Kepler 11f orbits a Sun-like star and is about 4 times the size of Earth. Another example is K2-18b, which has garnered significant interest due to its potential to harbor a habitable environment, although this is still a topic of ongoing research. The formation of mini-Neptunes is believed to involve processes similar to those that form other types of planets, but with distinct characteristics. One leading theory suggests that mini-Neptunes form in the protoplanetary disk around a young star, where they accrete a significant amount of gas and dust. This accretion process can lead to the formation of a dense core surrounded by a substantial envelope of hydrogen and helium. The exact composition of mini-Neptunes can vary, but they are often thought to have a rocky core with a thick atmosphere composed of hydrogen, helium, and possibly other volatile compounds. The presence of this thick atmosphere sets them apart from rocky planets like Earth and Mars. Comparing mini-Neptunes to other planet classes reveals interesting differences and similarities. For instance, mini-Neptunes are larger and more massive than super-Earths, which are planets with masses and radii larger than Earth, but smaller than Neptune. Super-Earths are often considered to be rocky planets, while mini-Neptunes are thought to have a significant gaseous component. This distinction is crucial for understanding the potential habitability of these planets. The thick atmospheres of mini-Neptunes can create extreme surface conditions, making them less likely to support life as we know it. However, the study of mini-Neptunes is still in its early stages, and new discoveries could challenge our current understanding. The study of mini-Neptunes is not just about understanding their formation and composition. It also provides valuable insights into the diversity of planetary systems and the processes that shape them. By comparing mini-Neptunes to other planet classes, astronomers can refine their models of planetary formation and evolution. This, in turn, helps us better understand our own solar system and the potential for life elsewhere in the universe. The ongoing exploration of mini-Neptunes and other exoplanets is a testament to the exciting and rapidly evolving field of astrophysics. Characteristics of mini-Neptunes. Mini-Neptunes are a fascinating class of exoplanets that have captured the attention of astronomers and astrophysicists alike. These planets are typically defined by their size, which is larger than Earth but smaller than Neptune, ranging from about 2 to 10 Earth radii. They are often found orbiting close to their host stars, with short orbital periods. One notable example is Kepler 11F, a planet discovered by the Kepler Space Telescope, which has a radius about 2.5 times that of Earth and orbits its star in just under 50 days. Mini-Neptunes are thought to have a thick hydrogen-helium atmosphere, which can be several times the mass of the planet's solid core. This atmosphere is likely the result of the planet's formation process, where it accreted gas from the protoplanetary disk. The composition of these planets is a subject of ongoing research, but they are generally believed to have a rocky or icy core surrounded by a substantial envelope of gas. The formation theories of mini-Neptunes are still being refined, but they are generally thought to form in a similar way to gas giants like Jupiter and Neptune. These planets likely start as a solid core that accretes gas from the surrounding protoplanetary disk. However, unlike gas giants, mini-Neptunes may not have enough mass to accrete a significant amount of hydrogen and helium, or they may form further from their star and migrate inward. This migration could be due to interactions with other planets or the protoplanetary disk itself. The Kepler mission has provided a wealth of data on mini-Neptunes, revealing that they are quite common in our galaxy. In fact, they are one of the most common types of planets found by the Kepler telescope. Their prevalence suggests that they play a significant role in planetary system formation and evolution. Comparing mini-Neptunes to other planet classes reveals some interesting differences. For instance, they are larger than Earth-like planets, but smaller than ice giants like Neptune and Uranus. Their thick atmospheres set them apart from terrestrial planets, which have much thinner atmospheres. Mini-Neptunes also differ from gas giants in their composition and size. While gas giants are primarily composed of hydrogen and helium, mini-Neptunes have a more significant solid core. This core could be rocky or icy, depending on the planet's formation history and location in the protoplanetary disk. The study of mini-Neptunes is crucial for understanding the diversity of planetary systems and the processes that lead to their formation. As our understanding of these planets grows, so too does our ability to contextualize the place of our own solar system within the broader galaxy. Formation of mini-Neptunes. Mini-Neptunes, also known as sub-Neptunes, are a class of exoplanets with masses and radii between those of Earth and Neptune. These planets are typically 2 to 4 times the size of Earth and have a composition that is likely a mix of rock, water, and volatile gases. Notable examples include Kepler 11F and GJ 3470b. Their formation is thought to involve the accretion of a rocky core followed by the accumulation of a significant envelope of hydrogen and helium gas. This process can occur in the protoplanetary disk, where the planet's gravity pulls in surrounding gas and dust. The exact mechanisms and timescales of this formation are still subjects of ongoing research, with theories suggesting that these planets may form quickly, within a few million years, or more slowly, over tens of millions of years. The formation of mini-Neptunes is closely linked to the availability of gas and solids in the protoplanetary disk. In regions where the disk is rich in both, mini-Neptunes can grow rapidly. The presence of water and other volatiles can also play a crucial role, as these substances can enhance the planet's ability to accrete gas. Additionally, the location within the disk affects the planet's composition. Closer to the star, the higher temperatures can lead to the formation of denser, rockier planets, while farther out, the cooler temperatures allow for the retention of more volatile materials. This gradient in composition is evident in the diversity of mini-Neptunes observed, with some having thick atmospheres and others being more rocky. Comparing mini-Neptunes to other planet classes reveals distinct differences in size, composition, and formation history. Super-Earths, for instance, are larger than Earth but smaller than mini-Neptunes, with masses up to 10 times that of Earth. They are primarily rocky, with some possibly having thin atmospheres. In contrast, mini-Neptunes have a significant gaseous envelope, making them less dense. The formation of super-Earths is thought to involve the accretion of rocky material without a substantial gas envelope, possibly due to the lack of available gas or the planet's proximity to the star. This distinction highlights the diverse pathways planets can take during their formation and evolution. Understanding these differences is crucial for comprehending the broader picture of planetary systems and their formation. Detection methods for mini-Neptunes. Mini-Neptunes, a class of exoplanets with masses and radii larger than Earth's but smaller than Neptune's, have been a subject of intense study. These planets are typically between 2 to 10 Earth masses and 2 to 4 Earth radii. Their detection has been primarily achieved through the transit method and the radial velocity method. The transit method involves observing the dimming of a star's light as a planet passes in front of it. This technique is particularly effective for detecting mini-Neptunes around smaller, cooler stars where the signal is more pronounced. For instance, the Kepler Space Telescope has identified numerous mini-Neptunes using this method. The radial velocity method, on the other hand, detects the wobble of a star caused by the gravitational pull of an orbiting planet. This method is less sensitive to smaller planets, but can provide crucial data on their mass and orbit. Formation theories for mini-Neptunes suggest they form in the protoplanetary disk, where they accrete a significant amount of gas and ice. Unlike terrestrial planets, which are primarily composed of rock and metal, mini-Neptunes have a substantial envelope of hydrogen and helium. This composition makes them distinct from super-Earths, which are rocky planets with masses and radii larger than Earth's but smaller than Neptune's. Super-Earths, such as 55 Cancri, are thought to form closer to their host stars, where the protoplanetary disk is hotter and more depleted of volatiles. In contrast, mini-Neptunes like Kepler 11F are believed to form further out, where ices and gases are more abundant. The distinction between these two classes of planets is crucial for understanding planetary formation and evolution. Comparing sizes and compositions, mini-Neptunes are generally larger and more massive than super-Earths. Their compositions include a significant fraction of volatiles, such as water, ammonia, and methane, in addition to their rocky cores. This makes them more akin to ice giants like Neptune and Uranus in our solar system. Super-Earths, however, are more similar to Earth and Venus, with compositions dominated by rock and metal. The boundary between these two classes is not always clear-cut, as some planets may have intermediate compositions. For example, the planet GJ1214b, with a radius of about 2.7 Earth radii, has been classified as a mini-Neptune but exhibits characteristics that blur the line between mini-Neptunes and super-Earths. Understanding these distinctions and overlaps is essential for refining models of planetary formation and evolution. Notable examples of mini-Neptunes. Mini-Neptunes, a relatively new class of planets, are typically defined as exoplanets with sizes ranging between 2 to 4 Earth radii and masses between 5 to 10 Earth masses. These planets are thought to have thick hydrogen-helium atmospheres, similar to Neptune, but orbiting much closer to their host stars. One notable example is Kepler 11F, which is part of a tightly packed planetary system. Kepler 11F has a radius about 2.5 times that of Earth and orbits its star in just under 50 days. Another example is Kepler 36c, which is part of a binary planet system with Kepler 36b. Kepler 36c has a radius about 3.7 times that of Earth and orbits its star every 16 days. These planets provide valuable insights into planetary formation and evolution, particularly how planets migrate within their systems. The formation of mini-Neptunes is still a topic of ongoing research. One leading theory suggests that these planets form beyond the snow line, where volatile ices can condense and then migrate inward due to interactions with the protoplanetary disk or other planets. This inward migration could explain why mini-Neptunes are often found in close orbits around their host stars. Another theory proposes that mini-Neptunes form in situ, meaning they form where they are currently located. This would require a high surface density of solids in the protoplanetary disk to allow for the rapid accretion of a significant atmosphere. The composition of mini-Neptunes is also a subject of interest. They are believed to have rocky cores surrounded by thick layers of hydrogen and helium, with possible water or other volatile ices. Comparing mini-Neptunes to other planet classes reveals distinct differences. Super-Earths, for instance, are planets with masses between 1 to 10 Earth masses and radii up to 1.5 times that of Earth. They are thought to have diverse compositions, ranging from rocky planets with thin atmospheres to planets with substantial water content. In contrast, mini-Neptunes are larger and have more massive atmospheres. The boundary between super-Earths and mini-Neptunes is not clearly defined, and some planets may fall into a transitional category. For example, Kepler 138d, with a radius about 1.5 times that of Earth, is often considered a mini-Neptune, but its mass and composition are still being studied. Understanding these differences and similarities is crucial for comprehending the diversity of planetary systems and the processes that shape them. The study of mini-Neptunes has been significantly advanced by missions like NASA's Kepler and Transiting Exoplanet Survey Satellite, TESS. These missions have identified numerous mini-Neptunes, providing a wealth of data for scientists to analyze. For instance, Kepler 444c is a mini-Neptune orbiting a K-type star with a radius about 2.3 times that of Earth. It orbits its star every 4.5 days, making it one of the closest known mini-Neptunes to its host star. Another example is TOI 270c, discovered by TESS, which has a radius about 2.4 times that of Earth and orbits its star every 5.7 days. These discoveries highlight the prevalence of mini-Neptunes in the galaxy and their importance in understanding planetary formation and evolution. Future missions, such as the James Webb Space Telescope, will further enhance our ability to study these intriguing worlds. Habitability of mini-Neptunes. In the vast expanse of the cosmos, astronomers have recently identified new classes of planets that challenge our traditional understanding of planetary systems. Super-Earths, as the name suggests, are planets with masses greater than Earth's, but significantly smaller than that of ice giants like Uranus and Neptune. These planets can be rocky or have a composition similar to that of gas giants. Examples of super-Earths include Kepler 442b and LHS 1140b, which orbit within the habitable zones of their respective stars, making them intriguing targets for the search for extraterrestrial life. Mini-Neptunes, on the other hand, are smaller versions of ice giants, with masses ranging from about 2 to 10 Earth masses. They typically have thick hydrogen-helium atmospheres and are thought to be common in the galaxy. Examples include Kepler 11f and GJ 3470b. The formation of these new classes of planets is still a topic of ongoing research. Super-Earths are believed to form in the protoplanetary disk through the accretion of solid materials, similar to Earth, but with more abundant materials leading to larger sizes. Some theories suggest that they may form closer to their stars, where the disk is denser, allowing for more rapid growth. Mini-Neptunes, however, are thought to form further out in the disk, where ices can condense and contribute to their growth. They may then migrate inward due to interactions with the protoplanetary disk or other planets. The exact mechanisms of their formation and migration are complex and involve a delicate balance of gravitational interactions, disk dynamics, and planetary growth processes. Comparing the sizes and compositions of super-Earths and mini-Neptunes reveals a fascinating diversity in planetary characteristics. Super-Earths can range from being predominantly rocky, like Earth, to having significant amounts of water or other volatiles, leading to a variety of possible surface conditions. Their sizes can vary, but they generally have radii between 1.25 and 2 times that of Earth. Mini-Neptunes, in contrast, are typically larger, with radii between 2 and 4 times that of Earth. Their compositions are dominated by hydrogen and helium, with possible layers of ices and rocky material beneath their thick atmospheres. This diversity in size and composition suggests a wide range of potential environments, some of which might be conducive to life. When considering the habitability of mini-Neptunes, several factors come into play. The thick atmospheres of mini-Neptunes present both opportunities and challenges for life. On one hand, these atmospheres could provide a protective shield against harmful radiation and help regulate surface temperatures. On the other hand, the high pressure and density of these atmospheres could make it difficult for life as we know it to thrive. Additionally, the presence of a substantial atmosphere could lead to extreme greenhouse effects, potentially rendering the surface too hot for liquid water to exist. However, recent studies suggest that some mini-Neptunes might have rocky cores with conditions suitable for life. For instance, the planet K2-18b, a mini-Neptune, has been found to have water vapor in its atmosphere, sparking interest in its potential habitability. The search for life on these planets remains a challenging endeavor, requiring advanced observational techniques and a deeper understanding of their atmospheric and internal structures. Comparative analysis: super-Earths versus mini-Neptunes. Super-Earths and mini-Neptunes represent two intriguing classes of exoplanets that have captivated astronomers due to their unique characteristics and the mysteries they present. Super-Earths, as the name suggests, are planets with masses ranging from slightly more than Earth's to about 10 times that of Earth. Examples of super-Earths include Kepler 442b and LHS 1140b. These planets are typically rocky, with some potentially harboring thick atmospheres. Their sizes and compositions make them prime candidates for hosting life, as they could have surface conditions suitable for liquid water. Mini-Neptunes, on the other hand, are smaller versions of our solar system's ice giant, Neptune. They have masses ranging from about 10 to 50 times that of Earth. Examples include Kepler 11f and GJ 3470b. These planets are enveloped in thick hydrogen and helium atmospheres, with possible layers of ice and rock beneath. Their compositions suggest they are more akin to miniaturized gas giants rather than terrestrial planets. The formation theories for super-Earths and mini-Neptunes differ significantly. Super-Earths are believed to form in the inner regions of protoplanetary disks, where the material is denser and more conducive to the accretion of rocky material. They may form from the collision and merger of smaller rocky bodies. Mini-Neptunes, however, are thought to form further out in the disk, where ices and gases are more abundant. They likely begin as rocky or icy cores that accrete enough gas to form substantial atmospheres. The distinction in formation locations and processes contributes to their differing compositions and structures. Understanding these formation pathways is crucial for comprehending the diversity of planetary systems and the potential habitability of exoplanets. Comparing the sizes and compositions of super-Earths and mini-Neptunes reveals stark contrasts. Super-Earths typically have radii between 1.25 and 2 times that of Earth, with densities suggesting rocky interiors. Their compositions can vary, with some having thin atmospheres and others possessing extensive ones. Mini-Neptunes, in contrast, have radii between 2 and 4 times that of Earth, with lower densities indicative of significant atmospheric envelopes. The compositions of mini-Neptunes are dominated by hydrogen and helium, with possible layers of ice and rock beneath. This difference in composition has profound implications for their internal structures and potential habitability. Super-Earths, with their rocky interiors, are more likely to have solid surfaces and stable conditions suitable for life. Mini-Neptunes, with their thick atmospheres, are less likely to have solid surfaces and may experience extreme conditions that are inhospitable to life as we know it. The study of super-Earths and mini-Neptunes continues to evolve as new data from missions like NASA's Kepler and TESS, as well as ground-based observatories, provide more insights into these enigmatic worlds. Each discovery brings us closer to understanding the formation and evolution of planetary systems, as well as the potential for life beyond our solar system. The comparative analysis of these two classes of planets highlights the diversity of exoplanets and the complex processes that shape their characteristics. As our knowledge grows, so too does our appreciation for the vast and varied nature of the cosmos. Size and mass differences. In the vast expanse of the cosmos, astronomers have recently identified new classes of planets that challenge our traditional understanding of planetary formation and composition. Among these, super-Earths and mini-Neptunes stand out, offering intriguing insights into the diversity of exoplanets. Super-Earths are rocky planets with masses ranging from a few Earth masses to about 10 times that of Earth. Examples include Kepler 442b and LHS 1140b, which orbit within the habitable zones of their respective stars. Mini-Neptunes, on the other hand, are gaseous planets with masses similar to or slightly larger than Earth, but with compositions more akin to Neptune. GJ 3470b and Kepler 11f are notable examples of this class. These planets are typically enveloped in thick atmospheres, primarily composed of hydrogen and helium. The formation theories of super-Earths and mini-Neptunes are still subjects of intense study. Super-Earths are believed to form from the accretion of rocky material in the protoplanetary disk, similar to Earth but on a larger scale. Their higher masses suggest that they may have formed closer to their stars, where the disk was denser, allowing for more material to coalesce. Mini-Neptunes, however, are thought to form further out in the disk, where ices and gases are more abundant. They may have migrated inward over time, driven by gravitational interactions with other planets or the protoplanetary disk itself. This inward migration could explain their presence in close orbits around their host stars. Comparing the sizes and compositions of super-Earths and mini-Neptunes reveals striking differences. Super-Earths, despite their name, are not simply larger versions of Earth. They exhibit a wide range of densities, indicating varied compositions that include significant amounts of water, volatiles, and even substantial atmospheres in some cases. For instance, Kepler 442b is estimated to have a radius about 1.3 times that of Earth, but a mass nearly 3 times greater, suggesting a dense, rocky composition. Mini-Neptunes, conversely, have lower densities due to their substantial atmospheres. GJ 3470b, for example, has a radius about 4.5 times that of Earth, but a mass only about 13.6 times greater, indicating a low-density, gas-rich structure. These differences highlight the complexity of planetary formation and the diverse outcomes that can arise from the same fundamental processes. Compositional variations. In the vast expanse of the cosmos, astronomers have recently identified new classes of planets that challenge our traditional understanding of planetary formation and composition. Super-Earths and mini-Neptunes are two such classes that have piqued the interest of scientists and space enthusiasts alike. Super-Earths are planets with masses ranging from a few Earth masses to about 10 times that of Earth, but they are not necessarily Earth-like. They can be rocky, but their compositions can vary widely, including significant amounts of water or other volatiles. Examples of super-Earths include Kepler 442b and LHS 1140b, which orbit within the habitable zones of their respective stars, making them intriguing targets in the search for life beyond our solar system. Mini-Neptunes, on the other hand, are planets with masses similar to Neptune but are much smaller. They are typically between 2 to 10 Earth masses and have thick hydrogen-helium atmospheres. Unlike gas giants, mini-Neptunes do not have a solid surface. Instead, their compositions are a mix of rock, water, and ices, enveloped in a dense atmosphere. Kepler 11f and GJ 3470b are notable examples of mini-Neptunes. These planets are often found orbiting close to their host stars, leading to high temperatures and unique atmospheric dynamics. The formation theories of super-Earths and mini-Neptunes are still subjects of ongoing research. One prevalent theory suggests that these planets form in the protoplanetary disk through the accretion of solid materials and gases. For super-Earths, the process might involve the collision and merger of smaller rocky bodies, followed by the accumulation of a significant atmosphere. Mini-Neptunes, however, are thought to form further out in the disk, where ices and volatiles are more abundant. They then migrate inward due to gravitational interactions with other bodies or the protoplanetary disk itself. This inward migration explains their close orbits around their host stars. Comparing the sizes and compositions of super-Earths and mini-Neptunes reveals fascinating insights into planetary diversity. Super-Earths can be up to twice the size of Earth, but with a more varied composition, including rocky cores with substantial atmospheres or even global oceans. Mini-Neptunes, while smaller than Neptune, share similar atmospheric characteristics but lack a solid surface. Their compositions are a blend of rock, water, and ices, making them distinct from both terrestrial and gas giant planets. Understanding these differences is crucial for comprehending the wide range of planetary systems in our galaxy and the potential for habitability beyond our solar system. Atmospheric properties. Super-Earths and mini-Neptunes are two new classes of planets that have captured the imagination of astronomers and the public alike. Super-Earths are planets with masses ranging from about 1 to 10 Earth masses, while mini-Neptunes are slightly larger, with masses between 10 and 18 Earth masses. These planets are not found in our solar system, but they are common in the galaxy. Kepler 442b and LHS 1140b are examples of super-Earths. Examples of mini-Neptunes include Kepler 11d and Kepler 11e. Formation theories suggest that super-Earths form in the protoplanetary disk through accretion of solid materials, while mini-Neptunes may form further out, where ices can contribute to their growth. Their sizes and compositions vary, with super-Earths likely having rocky interiors and mini-Neptunes possessing thick gaseous envelopes. Atmospheric properties of these planets are diverse and intriguing. Super-Earths can have a range of atmospheres, from thin and rocky to thick and gaseous. Some may even have atmospheres rich in water vapor, hinting at potential habitability. Mini-Neptunes, on the other hand, are expected to have substantial hydrogen-helium atmospheres, similar to but smaller than those of ice giants in our solar system. The atmospheric composition can provide clues about the planet's formation and evolution. For instance, a high metallicity in the atmosphere might indicate significant accretion of ices and solids during formation. These atmospheres can also influence the planet's climate and potential habitability. Comparing the atmospheric properties of super-Earths and mini-Neptunes reveals stark contrasts. Super-Earths with thin atmospheres might have surface conditions more akin to Earth, while those with thick atmospheres could experience intense greenhouse effects. Mini-Neptunes, with their substantial gaseous envelopes, likely have high surface temperatures and pressures, making them inhospitable to life as we know it. However, the study of these atmospheres is still in its infancy. Future observations, particularly with advanced telescopes like the James Webb Space Telescope, will provide more detailed insights into their compositions and dynamics. Understanding these atmospheric properties is crucial for determining the habitability and potential for life on these distant worlds. Orbital characteristics. Super-Earths and mini-Neptunes represent two fascinating classes of exoplanets that have reshaped our understanding of planetary systems. Super-Earths are planets with masses ranging from slightly more than Earth's to about 10 times its mass. Examples include Kepler 442b and LHS 1140b. These planets often orbit within the habitable zones of their stars, making them prime candidates in the search for life beyond our solar system. Mini-Neptunes, on the other hand, are smaller versions of Neptune, typically with masses between 10 and 30 Earth masses. They often have thick hydrogen-helium atmospheres and are found orbiting close to their host stars. Notable examples include Kepler 11f and GJ 3470b. Both classes challenge traditional planetary formation theories, suggesting that our solar system might be an outlier rather than the norm. The orbital characteristics of super-Earths and mini-Neptunes provide crucial insights into their formation and evolution. Super-Earths often exhibit relatively short orbital periods, ranging from a few days to several months. This proximity to their host stars can lead to tidal locking, where one side of the planet perpetually faces the star, creating extreme temperature differences. Mini-Neptunes, while also close to their stars, can have more varied orbital periods. Their thick atmospheres can lead to significant atmospheric escape, particularly in the intense radiation environments of close orbits. Both types of planets frequently reside in multi-planet systems, often in resonant orbits where their gravitational interactions stabilize their paths. Formation theories for these planets remain a topic of active research. Super-Earths are thought to form from the accretion of rocky material, similar to Earth, but with more abundant raw materials. Alternatively, they might form from the collision and merger of smaller protoplanets. Mini-Neptunes likely form further from their stars, where ices and gases are more abundant, and then migrate inward due to gravitational interactions with other bodies. Their thick atmospheres suggest they accreted significant amounts of gas during their formation. The discovery of these planets has highlighted the diversity of planetary systems and the need for refined models of planet formation and evolution. Understanding their orbital characteristics helps astronomers piece together the dynamic histories of these exotic worlds. Planetary systems and occurrence. In the vast expanse of the cosmos, astronomers have identified two intriguing classes of exoplanets, super-Earths and mini-Neptunes. These planets, which do not have direct counterparts in our solar system, have sparked considerable interest due to their unique characteristics and prevalence in the galaxy. Super-Earths are planets with masses ranging from slightly more than Earth's to about 10 times that of Earth. Examples include Kepler 442b, which orbits within the habitable zone of its star, and 55 Cancri e, known for its likely lava-covered surface. Mini-Neptunes, on the other hand, are planets with masses and radii larger than Earth's, but smaller than Neptune's. They often possess thick hydrogen-helium atmospheres. Notable examples include Kepler 11f and GJ 3470b, which exhibit significant atmospheric envelopes. The formation of these planets is still a subject of ongoing research. Super-Earths are believed to form in a manner similar to Earth, through the accretion of solid materials. However, their larger sizes suggest that they may have formed in regions with higher concentrations of heavy elements or experienced more efficient accretion processes. Mini-Neptunes, with their substantial atmospheres, are thought to have formed beyond the snow line, where volatile ices could condense and contribute to their growth. They may have migrated inward to their current orbits, a process influenced by gravitational interactions within their planetary systems. The diversity in their compositions and sizes indicates a complex interplay of factors during their formation and evolution. Comparing the sizes and compositions of super-Earths and mini-Neptunes reveals distinct differences. Super-Earths typically have radii between 1.25 and 2 times that of Earth and are predominantly rocky, though some may have significant water content. Their compositions can vary widely, from dense, Earth-like planets to those with extended atmospheres. Mini-Neptunes, with radii ranging from 2 to 4 times that of Earth, are characterized by their thick atmospheres, which can constitute a significant fraction of their total mass. These atmospheres are often enriched with elements heavier than hydrogen and helium, suggesting a complex formation history. The boundary between super-Earths and mini-Neptunes is not always clear, as some planets may fall into a transitional category, exhibiting characteristics of both. The occurrence of super-Earths and mini-Neptunes in planetary systems is a fascinating aspect of exoplanetary science. Observations from missions like NASA's Kepler and TESS have shown that these planets are quite common, particularly around stars smaller than our Sun's super-Earths often reside in the inner regions of their systems, while mini-Neptunes can be found at various distances from their host stars. Their prevalence suggests that the processes leading to their formation are efficient and widespread. Understanding the occurrence and distribution of these planets provides valuable insights into the diversity of planetary systems and the potential for habitable worlds beyond our solar system. Theoretical models and simulations. In the vast expanse of the cosmos, astronomers have identified new classes of planets that challenge our traditional understanding of planetary systems. Among these, super-Earths and mini-Neptunes stand out, captivating scientists with their unique characteristics. Super-Earths are rocky planets with masses greater than Earth's, but significantly smaller than ice giants like Neptune. Examples include Kepler 442b and LHS 1140b, which orbit within the habitable zones of their respective stars. Mini-Neptunes, on the other hand, are gaseous planets with masses ranging from a few Earth masses up to Neptunes. These planets, such as Kepler 186f and GJ 3470b, have thick hydrogen-helium atmospheres and are often found in the inner regions of their planetary systems. The formation of these exotic worlds remains a topic of intense study. Theoretical models suggest that super-Earths form through the accretion of rocky material in the protoplanetary disk, similar to Earth, but with more abundant material. Some theories propose that they may have migrated inward from colder regions, where icy materials could contribute to their growth. Mini-Neptunes, however, are thought to form further out in the disk, where ices and gases are more abundant. These planets likely undergo significant migration, moving inward to their current orbits. The exact mechanisms driving these migrations are still being explored, with gravitational interactions with other planets and the protoplanetary disk playing crucial roles. Comparing sizes and compositions reveals striking differences between super-Earths and mini-Neptunes. Super-Earths typically have radii between 1.25 and 2 times that of Earth, with densities indicating a rocky composition. Their surfaces may be rich in silicates and metals, potentially hosting atmospheres that could support life under the right conditions. Mini-Neptunes, in contrast, have radii ranging from 2 to 4 times Earth's, with lower densities suggestive of thick atmospheres. These atmospheres can be hundreds to thousands of kilometers deep, composed primarily of hydrogen and helium, with possible layers of water, ammonia, and methane ices. The interplay between their rocky cores and gaseous envelopes makes mini-Neptunes particularly intriguing subjects for atmospheric studies. Simulations have been instrumental in understanding the dynamics and evolution of these planetary classes. Advanced computational models allow scientists to explore the formation and migration of super-Earths and mini-Neptunes within protoplanetary disks. These simulations consider factors such as disk density, temperature gradients, and the presence of other planetary bodies. By running multiple scenarios, researchers can identify common formation pathways and the conditions that lead to the observed diversity in exoplanetary systems. For instance, simulations have shown that the presence of giant planets can significantly influence the migration of super-Earths and mini-Neptunes, either facilitating their inward journey or halting it altogether. This interplay of gravitational forces shapes the final architecture of planetary systems, providing insights into the prevalence and distribution of these new planet classes. Observational challenges. Super-Earths and mini-Neptunes represent 2 intriguing classes of exoplanets that have reshaped our understanding of planetary diversity. Super-Earths are planets with masses ranging from slightly more than Earth's to about 10 times Earth's mass. Examples include Kepler 442b and LHS 1140b, which orbit within the habitable zones of their respective stars. Mini-Neptunes, on the other hand, are planets with masses similar to Neptune but much smaller radii, typically between 2 to 4 Earth radii. These planets, like K2-18b and TOI 270c, often possess thick atmospheres rich in hydrogen and helium. The formation theories for these planets suggest that super-Earths may form through the accretion of rocky material, while mini-Neptunes might originate from the rapid accretion of gas onto a rocky core. Their sizes and compositions vary significantly, with super-Earths often being rocky or having a significant fraction of water, whereas mini-Neptunes are likely to have substantial gaseous envelopes. Observing these planets presents unique challenges due to their distant and often faint nature. The primary method for detecting exoplanets, the transit method, relies on measuring the tiny dip in a star's brightness as a planet passes in front of it. However, the transit depth for super-Earths and mini-Neptunes is often minimal, making detection difficult without highly sensitive instruments. Radial velocity measurements, which detect the wobble of a star caused by an orbiting planet, also face limitations. The signals from these planets are subtle, requiring precise instruments and long observation periods. Additionally, the atmospheres of mini-Neptunes can obscure their surfaces, making it hard to determine their exact compositions. These observational hurdles necessitate advanced technologies and innovative techniques to study these enigmatic worlds. Despite these challenges, astronomers have made significant progress in characterizing super-Earths and mini-Neptunes. Spectroscopic analysis of transit spectra has revealed the atmospheric compositions of some mini-Neptunes, providing insights into their formation and evolution. For instance, K2-18b has been found to have water vapor in its atmosphere, hinting at a potential ocean beneath its thick hydrogen-rich envelope. Super-Earths, like LHS 1140b, have been studied for their potential habitability, with some showing promising conditions for liquid water on their surfaces. The James Webb Space Telescope, JWST, and upcoming missions like the European Space Agency's Plato, planetary transits, and oscillations of stars mission are expected to revolutionize our understanding of these planets by providing more detailed observations and data. These advancements will help unravel the mysteries of super-Earths and mini-Neptunes, offering a deeper understanding of planetary formation and the potential for life beyond our solar system. Future missions and technologies. The discovery of super-Earths and mini-Neptunes has opened up new avenues in planetary science, pushing the boundaries of our understanding of planetary formation and evolution. Super-Earths, as the name suggests, are planets with masses greater than Earth's, but significantly less than that of ice giants like Neptune. Examples include Kepler 442b and LHS 1140b. These planets often exhibit a rocky composition, but their larger size allows for a wider range of atmospheric conditions. Mini-Neptunes, on the other hand, are smaller versions of gas giants like Neptune, with masses ranging from about 2 to 10 Earth masses. GJ 3470b and Kepler 11d are notable examples. These planets typically have thick hydrogen-helium atmospheres, but their smaller size compared to Neptune suggests a more diverse internal structure. The formation of these new classes of planets is still a topic of ongoing research. One prevalent theory suggests that super-Earths form in the protoplanetary disk through the accretion of rocky material, similar to Earth, but with more abundant material available. This process can lead to a variety of outcomes, from rocky planets with thin atmospheres to those with substantial volatile envelopes. Mini-Neptunes, however, are thought to form further from their host stars, where ices and gases are more abundant. They may migrate inward over time, driven by gravitational interactions with other planets or the protoplanetary disk. The exact mechanisms of their formation and migration are complex and require detailed modeling and observation. Comparing the sizes and compositions of super-Earths and mini-Neptunes reveals significant differences. Super-Earths typically have radii between 1.25 and 2 times that of Earth, with densities indicating a rocky or mixed rocky-icy composition. Their atmospheres can vary widely, from thin and Earth-like to thick and hydrogen-rich. Mini-Neptunes, with radii between 2 and 4 times that of Earth, are less dense and have substantial atmospheres composed primarily of hydrogen and helium. The boundary between super-Earths and mini-Neptunes is not clearly defined, and some planets may fall into a transitional category, exhibiting characteristics of both. Understanding these differences is crucial for predicting their habitability and potential for hosting life. Future missions and technologies aim to delve deeper into the mysteries of these exotic worlds. The James Webb Space Telescope, JWST, with its advanced infrared capabilities, is poised to study the atmospheres of super-Earths and mini-Neptunes in unprecedented detail. By analyzing the spectral signatures of these atmospheres, scientists hope to detect biomarkers and understand the chemical processes at play. Additionally, upcoming missions like the European Space Agency's Aerial, Atmospheric Remote Sensing Infrared Exoplanet Large Survey are specifically designed to characterize the atmospheres of exoplanets, focusing on their composition, structure, and dynamics. Ground-based observatories, such as the Extremely Large Telescope, (ELT), and the Giant Magellan Telescope, (GMT), will further enhance our ability to directly image and study these distant worlds. These advancements will not only expand our knowledge of planetary systems, but also pave the way for future exploration and potential interstellar travel. Implications for planetary science. In the vast expanse of the cosmos, astronomers have recently identified 2 intriguing new classes of planets, super-Earths and mini-Neptunes. These planets challenge our traditional understanding of planetary formation and composition. Super-Earths, as the name suggests, are planets with a mass higher than Earth's, but significantly lower than that of ice giants like Uranus or Neptune. Examples include Kepler 442b and LHS 1140b. Mini-Neptunes, on the other hand, are smaller versions of Neptune, with masses ranging from about 2 to 10 Earth masses. Kepler 186f and HAT P 11b are notable examples of this class. Both types of planets are not found in our solar system, making them fascinating subjects of study. The formation theories of super-Earths and mini-Neptunes are still evolving. One prominent theory suggests that super-Earths form in the inner regions of protoplanetary disks, where the temperature is high enough to prevent volatile compounds from condensing. This leads to planets with rocky compositions, enriched with heavier elements. Mini-Neptunes, however, are thought to form further out, where volatile compounds can condense, resulting in planets with substantial atmospheres composed of hydrogen, helium, and other gases. The exact mechanisms of their formation remain a topic of ongoing research, with scientists using advanced models and observations to unravel the mysteries. Comparing the sizes and compositions of super-Earths and mini-Neptunes reveals striking differences. Super-Earths typically have radii ranging from about 1.25 to 2 times that of Earth, with densities indicating a rocky composition. Their surfaces may be solid, and they could potentially harbor liquid water, making them candidates for habitability. Mini-Neptunes, however, have radii between 2 to 4 times that of Earth and are less dense, suggesting a significant gaseous envelope surrounding a possible rocky core. This gaseous envelope makes them less likely to have solid surfaces, and their atmospheres are thought to be more extended and dynamic. The discovery of super-Earths and mini-Neptunes has profound implications for planetary science. These planets bridge the gap between the terrestrial planets of our solar system and the ice giants, providing valuable insights into planetary diversity. Studying their atmospheres, compositions, and formation processes can help scientists understand the conditions necessary for planet formation and the potential for habitability. Moreover, the prevalence of these planets in exoplanetary systems suggests that our solar system might be an outlier rather than the norm. This realization reshapes our understanding of planetary systems and the universe at large. Exoplanetary demographics. In the vast expanse of the cosmos, astronomers have discovered a menagerie of planets that challenge our traditional understanding of planetary systems. Among these, super-Earths and mini-Neptunes have emerged as 2 distinct classes, reshaping our views on planetary demographics. Super-Earths are planets with masses ranging from about 1 to 10 Earth masses, while mini-Neptunes are slightly larger, with masses between 10 to 30 Earth masses. These planets are not found in our solar system, making them fascinating subjects of study. Examples of super-Earths include Kepler 442b and LHS 1140b, whereas mini-Neptunes are represented by planets like Kepler 11d and HAT P 26b. The formation of these planets remains a topic of ongoing research. Super-Earths are believed to form in the protoplanetary disk through the accretion of solid materials, similar to Earth, but with more abundant materials leading to larger sizes. Some theories suggest they might form closer to their host stars, where the disk is denser. Mini-Neptunes, on the other hand, are thought to form further out in the disk, where ices and gases are more abundant. They likely start as rocky cores that accrete significant amounts of hydrogen and helium, leading to their larger sizes and substantial atmospheres. The exact mechanisms and timelines of these processes are still being unraveled. Comparing sizes and compositions reveals striking differences between super-Earths and mini-Neptunes. Super-Earths are typically rocky, with densities similar to or slightly higher than Earth's. Their surfaces might be habitable, depending on their atmospheres and distances from their stars. Mini-Neptunes, however, are enveloped in thick atmospheres of hydrogen and helium, with possible layers of supercritical fluids or ices beneath. Their compositions are more akin to Neptune and Uranus in our solar system, but on a smaller scale. The diversity in sizes and compositions among these exoplanets highlights the complexity of planetary formation and evolution. Understanding these new classes of planets is crucial for comprehending the demographics of exoplanetary systems. Surveys like those conducted by the Kepler and TESS missions have revealed that super-Earths and mini-Neptunes are quite common, especially around smaller, cooler stars. This prevalence suggests that our solar system, with its lack of such planets, might be an outlier rather than the norm. The study of these planets not only expands our knowledge of planetary science, but also fuels the search for potentially habitable worlds. Each discovery brings us closer to answering fundamental questions about the universe and our place within it. Broader implications for astrobiology. In the vast expanse of the cosmos, astronomers have recently identified two intriguing classes of exoplanets: super-Earths and Mini-Neptunes. Super-Earths are planets with masses ranging from a few Earth masses up to about 10 times that of Earth. Examples include Kepler 442b and LHS 1140b. These planets are typically rocky, but their larger size allows for a wider range of compositions, including significant amounts of water or ice. Mini-Neptunes, on the other hand, are planets with masses similar to Neptune but much smaller, often between 5 and 10 Earth masses. Examples include Kepler 11d and HAT P 26b. These planets are characterized by thick hydrogen-helium atmospheres and possibly substantial water or volatile-rich layers. The formation theories for these planets are still evolving. Super-Earths are thought to form in the protoplanetary disk through the accretion of rocky material, similar to Earth, but with more abundant material available. Some may form closer to their stars, where the disk is denser, allowing for more rapid growth. Mini-Neptunes likely form further out in the disk, where ices and gases are more abundant. They may migrate inward over time, bringing their volatile-rich compositions closer to their host stars. The exact mechanisms of their formation and migration are areas of active research. Comparing sizes and compositions reveals stark differences. Super-Earths are generally denser, with radii up to about 1.5 times that of Earth, and compositions that can include significant amounts of water or other volatiles. Mini-Neptunes, however, are less dense, with radii up to about 2.5 times that of Earth, and compositions dominated by light elements like hydrogen and helium. This distinction is crucial for understanding their potential habitability. Super-Earths, with their rocky surfaces, could have conditions suitable for life, while Mini-Neptunes, with their thick atmospheres, might be less hospitable. The broader implications for astrobiology are profound. Super-Earths, with their potential for diverse compositions and environments, offer a tantalizing opportunity to study planets that could harbor life. Their larger size means they could retain their atmospheres longer, providing more stable conditions for life to emerge and evolve. Mini-Neptunes, while less likely to be habitable, provide valuable insights into planetary formation and evolution. Studying these planets helps scientists understand the range of possible planetary systems and the conditions that might lead to the emergence of life. The discovery and study of these new classes of planets expand our understanding of the universe and our place within it. Public interest and media representation. In the realm of exoplanetary science, two intriguing classes of planets have captured significant public interest and media attention: super-Earths and Mini-Neptunes. These planets, which do not have direct analogs in our solar system, have sparked curiosity and fueled speculation about their potential habitability and unique characteristics. Super-Earths are planets with masses ranging from slightly more than Earth's to about 10 times that of Earth. Examples include Kepler 442b, often dubbed a super-habitable planet due to its potential to support life, and 55 Cancri e, a lava-covered world orbiting very close to its star. Mini-Neptunes, on the other hand, are planets with masses similar to Neptune's but much smaller, typically between 2 and 10 Earth masses. GJ 3470b and Kepler 11d are notable examples of this class. Their compositions are thought to be rich in ices and gases, with thick atmospheres enveloping potential rocky cores. The formation theories of these planets are as diverse as the planets themselves. Super-Earths are believed to form in the protoplanetary disk through accretion of solid materials, similar to Earth, but with more abundant materials leading to larger sizes. Some may have formed farther from their stars and migrated inward. Mini-Neptunes likely form in colder regions of the protoplanetary disk, where ices are abundant. They may have started as rocky cores that accreted significant amounts of gas and ice, or they could be the remnants of larger gas giants that lost their outer atmospheres. The exact processes are still under investigation, with scientists using advanced telescopes and computational models to unravel the mysteries of their origins. Comparing sizes and compositions reveals stark differences between these two classes. Super-Earths are typically rocky, with densities suggesting they have solid surfaces. Their compositions can vary widely, from Earth-like planets with iron cores and silicate mantles to carbon-rich worlds with graphite or diamond layers. Mini-Neptunes, however, are enshrouded in thick atmospheres composed mainly of hydrogen and helium, with possible layers of water, ammonia, and methane ices. Their densities are lower than super-Earths, indicating a significant fraction of their mass is in the form of gases. This distinction is crucial for understanding their potential habitability. While super-Earths might have conditions suitable for life, mini-Neptunes are less likely to support life as we know it, given their massive atmospheres and high pressures. Public interest in these planets is fueled by their potential to host life and the tantalizing possibility of discovering Earth-like conditions elsewhere in the universe. Media representation often highlights the exotic nature of these worlds, with vivid descriptions of lava oceans, diamond cores, and thick, swirling atmospheres. Documentaries, news articles, and even science fiction have played a role in popularizing these planets, making them household names. The media also plays a crucial role in communicating the scientific findings and the ongoing quest to understand these enigmatic worlds. However, it's essential to balance sensationalism with accurate information, ensuring that the public remains informed and engaged without being misled. As our understanding of super-Earths and mini-Neptunes continues to evolve, so too will the public's fascination with these distant, alien worlds. As we wrap up our journey through the fascinating worlds of super-Earths and mini-Neptunes, let's recap the key points. Super-Earths, like 55 Cancri, are rocky planets up to 10 times the mass of Earth, offering insights into planetary evolution and potential habitability. Mini-Neptunes, such as Kepler 11F, are gaseous planets with thick atmospheres, smaller than our own Neptune but larger than Earth. Their formation theories suggest they might have started as rocky cores that accumulated significant hydrogen and helium atmospheres. In terms of size and composition, super-Earths are denser and more Earth-like, while mini-Neptunes are less dense with substantial atmospheres. These differences hint at diverse formation histories and environmental conditions. Now, imagine standing on the surface of a super-Earth, feeling the pull of its stronger gravity, or floating in the thick atmosphere of a mini-Neptune, gazing at its swirling clouds. These worlds, though far away, invite us to ponder the vast possibilities of planetary diversity. If you're as captivated as we are, join us next time as we dive into another cosmic mystery. Perhaps we'll explore the enigmatic worlds of rogue planets or the icy moons of our outer solar system. Until then, keep looking up and wondering. The universe is full of surprises, and we're just getting started. Don't forget to like, share, and subscribe for more out-of-this-world adventures. Clear skies, everyone.